Today, we're going to start talking about cycles and thermochemical cycles to be a little bit more specific to that. And maybe that begs the question for this being an introductory class, what the heck is a thermochemical cycle? And my sort of definition for this is that it is a series of processes that manipulate the thermodynamic state, things like temperature, pressure, etc., volume, of a working fluid to do one of two things. So the first one is to convert thermal or chemical energy into useful work. And some typical examples to that are things like heat engines, right? Where we have a combustion, and that combustion drives the creation of mechanical work by usually turning a crankshaft. Another good example is electricity generation, where really what we're trying to do, and you'll see this during the course of the next couple of weeks, is to turn a turbine, right? So we're going to manipulate the chemical state of our system to do that. The second thing that we can do, right? We either can convert thermal or chemical energy into work. The second thing is to use work to extract thermal energy. Or expel thermal energy from the system and give it to the surroundings. And we have experience with those systems, right? They're things like refrigerators, air conditioners. And there are some really interesting parts to their operation that aren't really obvious at first, which I think is one of the things that makes the refrigeration part of cycles a little bit more difficult for us to comprehend. So we're going to tackle these in order. And the first one that we're going to talk about is this conversion of thermal or chemical energy into useful work. And just like when we started the very beginning of our class, first looking at the energy balance and the behavior of closed systems, and then we moved to open systems, we're going to do something very similar here. And one of the most common simplifications is that the working fluid operates in a closed system. And so if we tried to think about this, right? So let's think of what might happen in an engine if we treated it as a closed system. And maybe one of the ways that will show that this is even possible is I'll do a demonstration of a Stirling engine in a few lectures. But we're going to treat this at first like a closed system. And so if we think about this, what are the steps that you might have in a 4-step process or a 4-stroke heat engine if you already had contained the fluid? Well, the first step in that process, and the first step in almost all of these heat engine problems, is a compression. So step 1, we're going to do work, right? Or work is done to the system by the surroundings. And if you want to think about the physical part of this in a heat engine, it's when you initially have the fuel in the cylinder, and you actually compress it, right? So the piston cylinder comes all the way down, and the pressure goes up and the volume goes down. So if we wanted to look at this maybe as a picture on a PV diagram, here, maybe I'll make my V a little bit better. We might start somewhere over here on a PV diagram, and we're going to decrease the volume and increase the pressure. So we're going to go here, right? So this is kind of a normal step one, and this would be compression, right? And maybe since I already have it written up there, I'll just put 1. Then the second step in a real system is then combustion, right? That's when the spark plug ignites and the entire gas combusts. Now, if we want to talk a little bit about if the working fluid was already in the cylinder, you might not have a combustion, but like in a Stirling engine, for example, you can have, you can add heat from outside. So you have some heat addition that usually comes from the combustion of something. And so step 2 is almost always heat added to the system. And often by combustion, right? Doesn't have to be, but that's how most heat engines are going to work. And that's going to take us, to some other place up here, right? Where the volume's probably not going to change a lot, especially in a combustion. If you think about that, combustion happens in milliseconds. And so the volume won't change a lot during the course of that heat addition. So we're going to treat that, later, and actually in a minute, we'll treat that completely as isochoric, but it doesn't necessarily have to be perfectly isochoric. So then what happens after the combustion, or after we've added heat to the system very, very quickly? Well, the whole reason we did that, right, is because we want this crankshaft to spin, and you do that by pushing back on the piston cylinder. So you have an expansion. And that's when work is done by the system. Right? On the surroundings. And oftentimes, right, when you're going to do that, not oftentimes, every time you're going to do that, the pressure goes down and the specific volume goes up, right, because you're expanding the cylinder, right? So you'll have something like an expansion. And then the fourth step in all of these heat engines is, in a real heat engine, you actually would exhaust everything to the atmosphere, right? It comes out of a tailpipe, and then you would intake a new, some more air and some more gas. In a closed system, what we would do is we would just return to the initial state. And often that's just by removing heat. And we'll do a good example of that in a minute, okay? And so then we're kind of moving around this cycle from the initial volume through step 1, then through step 2, step 3, then to step 4. And the reason that it's called a cycle is because we're going to get to the exact same place that we started at the end. And so we will go in that cycle over and over and over again. Okay? So before I do anything else, I just want to open this up to questions.
Are steps 1 and 3 isothermal?
They don't have to be, but that's a really good question. So we will do an example of the Carno engine before the end of class today. And in the Carno engine, they are isothermal, but they do not have to be. Okay, and we'll do examples in class as well. We're going to do heat engines really for about the next 4 or 5 lectures, and we'll do examples where steps 1 and 3 are isothermal, and we will do steps where they're not isothermal. But very good question. Yeah, they can be, but they don't have to be.
So I have a question on number
Sure.
2. That heat is added to the system, but not always. What are some examples of the not always?
Oh no, in step 2, I said you don't always do that by combustion.
Okay.
You could add it through, like, one of the last examples we're going to do is a solar cycle. And that'd be a really good example of how you could add heat to the system and it not have to be from a combustion. You also could use resistive heat, although that would be incredibly inefficient. But yeah, it doesn't have to come from combustion, but often it does. Yeah, good question.
Sorry, that I was writing down and process all that.
No, that's okay. And one of the ways that like heat pumps work is if you were to run this cycle backwards, you're actually, sometimes you're even digging underground and you're just using geothermal sinks as sources for like to dump heat into, or like I said, solar thermal to take energy in. And in other seasons, you're going to run the heat pump as an actual, yeah, I guess when you run it as an actual heater, not as a refrigerator, you're actually taking heat from the ground and using it to heat up your house. So, I mean, that's another example. You're just using geothermal energy instead of a combustion. So yeah, there are some good examples. So anyway, that's really great. I'm glad that you guys asked both of those questions. So one of the things that I kind of want to make a big deal about, because we're going to do an example here where we take advantage of this fact. And actually, we're going to use this a lot in the next couple of weeks, is that at the end of the cycle, you are exactly at the beginning of the cycle, right? The end of step 4 and the beginning of step 1 are exactly the same. And that's important because if you think about this, we've asked questions this entire semester about, how does the enthalpy change as a function of temperature and pressure? How does the internal energy change as a function of temperature and pressure? How does entropy change as a function of temperature and pressure? And all of those are state functions. So the internal energy, the enthalpy, and entropy, these only depend on where you are, right? At what temperature or pressure you are. And so because of this, when you go around this presumably closed system, if you're at the same temperature and pressure at the end, delta U for a cycle is equal to 0, right? You're at the same temperature. And remember, the integral of CP/dt is equal to delta U. And that's valid not just for every individual step, but that's valid if you were to sum all of the individual steps. Okay, so delta U, when you go around the entire cycle, because you end up at the same place you started, that's equal to 0. But the interesting thing is that the work and the heat are not state functions. So Q and W are not state functions. And what that means is that you can't really calculate Q and W as, as functions of temperature and pressure. You do work and you exchange heat oftentimes, and we calculate temperature and pressure. But for Q and W, you are highly dependent on the path that you took to get there. And, let's assume for just a second, I actually can show you this visually, that let's say that that steps 1 and 3 were isochoric, that steps 2 and 4 were isochoric, and we're going to do this for Carno in a minute anyway, and steps 1 and 3 were isothermal. Well, if that were the case, then you would only have work done in steps 1 and 3. And just look at the area under the curve, right? Because it'd be the integral of PDV at constant t, right? So that would be the work that you had to do. And then this one here would be the work that you got out of this cycle, right? And thank goodness that the work that you get out is greater than the work that you put in. That's the whole point of what we're trying to do. But if you were to sum the work that was done in each one of these, in every step, right, the sum of the work would not be 0, right? You're going to, in this process, you are going to have a net production of work, which I think is really important for us to just acknowledge at the beginning, right? That Q and W are absolutely not state functions. So oftentimes, the sum of all the Q's for a cycle are not equal to 0. And the sum of all of the work that's done for a cycle is not equal to 0. They can be for an individual step. You could, by serendipity, have this happen, but generally it is absolutely not the case. And to show that, and maybe how we would apply this concept before we move on and talk about Carno, I wanted to do an example from the book, if that's okay with you guys. And
Dr. Mustaine, I have a quick question.
Sure.
So Q and W are not necessarily equal to 0 for a cycle, but the addition of the sum of the Q's and the sum of the W's would be equal to 0 because delta U equals 0.
No. So remember, our energy balance, right, is du is dq plus dw, right? So if I take the sum for all of these cycles, this becomes the sum of the delta U for each individual cycle is equal to the sum of the heat plus the sum of the work. This one is 0. But these are, oh, sorry, I wrote Q twice. Sorry, guys. But these two are not 0, right? And the reason for that, like I said, is that U is a state function. So if you go all the way around the cycle, you end up at the same place that you started. So the change in the internal energy, if you were to end and begin at the same place, is 0. But you had to do work and move heat around to get there. And so those are path dependent, whereas where things like entropy, enthalpy, and the internal energy are all state functions. Okay?
Okay, gotcha. Thank you.
All right, good. All right, so let's apply this concept, right, where delta U is going to be equal to 0 for a cycle, and that the sum of Q and the sum of the W's for an individual cycle are not going to be equal to 0. All right, so this problem is SVN 2.6, and it says that 1 mole of gas in a closed system undergoes a 4-step cycle. Use the data given in the table to determine the numerical values for the missing quantities indicated by the question marks. Okay, so I guess the very first way that I'll go about applying this is that we know that delta U for the entire cycle has to be equal to 0, right? And so let's go ahead and I'm going to get rid of that. And I'm going to put that in. Okay. Sorry, guys. Change the font color. And we know then delta U for that cycle is going to be equal to 0. Okay. Now, the interesting thing here is that, and maybe I shouldn't have erased it, that we immediately can put in at least a couple more values into this table. Because if we go back to here, and maybe I undo all of that erasing that I did, we got to a point, albeit somewhat messy, so let me get rid of the stuff I don't want to talk about here, right? That if delta U is equal to, if the sum of the internal energy around a cycle is equal to 0, that means that Q for a cycle, right, or the sum of all the Q's for the cycle equal minus the sum of all of the work that's done for a cycle, right? That's still just applying our energy balance and the fact that the internal energy is a state function. So if this is true, that Q and W have to be equal in magnitude but opposite in sign around this cycle, well, that means that we can actually immediately enter our value for Q for the overall cycle in the bottom row here, right? So this becomes equal to just, right, 1400 joules. So those are two relatively straightforward ones that we can implement. And now what we're going to do is for every other row where we have two values already there, we're going to take advantage of the fact that for any individual step, we still have a closed system, and delta U is equal to Q plus W. So I'm going to start here at the top. And if we know that delta U has to equal Q plus W, well, that means that 200 joules has to equal X plus negative 6,000. And so, of course, if here that's negative 6,000, then Q is equal to 5,800. And this will satisfy the energy balance, right? So if we added Q and W here, you would get minus 200. And you could apply the same concept here in the third row, where we're talking about step 3 to step 4, that we know that delta U for that individual step has to be equal to Q plus W. And so that's just minus 800 plus 300. And of course, that is just minus 500 joules.
Are you writing all that down?
No, you guys should be able to see the PowerPoint presentation, right? Where I'm typing.
Yeah. Okay.
Yeah. I'm not writing the notes down. I'm just typing them directly into the PowerPoint.
Cool. Thanks.
Yeah, no problem. Okay, so all right, I did a couple just as to get us going. So I'm going to let you guys jump in and help me to figure out what the last 4 question marks are going to be. So where do you guys want to go next?
Let's do the sum of the Q's.
Yeah, we can do that. And so here, maybe to help people out a little bit. So we know that the sum of the Q's is equal to 1,400 joules, right? And so then that's equal to Q in step 1 plus Q in step 2, or actually the way that this is written, it's a little bit different. So I'll actually be consistent. It's Q1 to 2 plus Q2 to 3 plus Q3 to 4 plus Q4 back to 1, right? The beginning of the cycle. And so 1,400 joules equals then 5,800, right? Which we calculated already, plus negative 3,800 plus negative 800 plus Q4 1. So what's that? So what's Q4 to 1 then equal to?
200 joules.
All right, so we have that Q4 to 1 equals 200 joules. And is everybody in agreement with that?
Yeah.
Yep. Okay. Just making sure we're all on the same page. All right. So let's do this. Let's go ahead and insert this on the left-hand side here. And that's minus 200. Okay, good. All right. So which one would you guys like to do next?
How about the sum of the delta U's?
All right. And actually, here, hold on one second. I made a mistake when I typed this, right? It's 200, not minus 200. Sorry, guys. That was my mistake. And I did it again. All right. Okay, good. So what was that? What was the next one that you guys wanted to do?
The sum of the change in internal energy.
Yeah, that's fine. And so then what do you guys have for delta U 2 to 3?
Negative 4,000.
All right, so we have, and if you look at that, I think that makes a lot of sense, right? Because 4 to 1 is 4,700. And then 1 to 2 is minus 200. The other one's minus 500. And the total has to be 0. So that's correct. That is equal to minus 4,000 joules. Good job. All right, great. And so now we just have these two, we have these, the two work terms left to do, right? And we know that delta U is equal to Q plus W. So if the change in the internal energy from 2 to 3 is minus 4,000 and Q is minus 3,800, that means that this has to be minus 200, correct? And then the last one is the work in step 4 to 1, and we'll solve that the exact same way, that we know that Q plus W equals delta U, and if Q is 200 and delta U is 4,700, we know then that this has to be 4,500, okay? And if you think about this, as we've done this, preliminary analysis around this cycle, we've only used really two pieces of information to help us get there. The first one was that delta U for the cycle is equal to 0. And the other one is that for any individual step, well, maybe we use three pieces of information. One, delta U for a cycle is equal to 0. Two, for any individual step, delta U is equal to Q plus W. And we're just saying that for every step, the first law is valid. And if you think about what we've done this semester, we've done a lot of single steps. And that was always true. And the third step is that for a cycle, so delta U of the cycle equals the sum of all the Q's for the cycle plus the sum of all the W's for the cycle. And of course, we already said that delta U for the cycle is equal to 0. And so these are three pieces of information that that we're going to use to solve for multiple cycles. Okay. All right. So before we go on to the an idealized cycle, does anybody want to ask any questions about this particular example problem or the three equations that we have here?
Yeah, so I have a little bit of just like a conceptual, just like clearing up my conceptual understanding. So
Sure.
really what we have going on is that we have the same amount of energy going in and out of the system, but we're converting some of the heat energy into work, and that's why we get a net work out.
Exactly. And if you think about the entire idea of a heat engine, that's exactly what we're doing, right? We want to convert heat into work. And so we actually hope that for the cycle, that will be positive, right? Or sorry, that will be negative, right? We're going to do more work than the heat that we put in. All right, and we'll have an interesting way, I think, to define those things in just a minute. Okay. All right, good. All right, anybody else? All right, if not, then let's talk about the most famous thermochemical cycle, hands down, and that is the Carno heat engine. Okay. And the Carno heat engine is a theoretical construct that cannot be physically replicated. And the reason for that is it assumes that that it's completely possible to decouple heat and work. So in the Carno heat engine, we're going to assume essentially every single step is reversible. We're going to assume that we have an ideal gas. We're going to assume that we have a closed system. We're also going to assume, and really the reason it can't be physically implemented, is that a Carno heat engine has three components. The first component is our system. Okay, so it is where our working fluid is located. And the other two components are heat reservoirs. So the first reservoir is cold, and the second one is hot. And really, they're just, one is at higher temperature, which is T, which we'll end up calling T sub H, and the other one is at a lower temperature, which we will call T sub C. And what's going to happen is that we're going to end up allowing the system to exist in a vacuum, right? Or not in a vacuum, but alone, isolated for some steps. And then you would physically move it to the hot or the cold reservoir to perform the other steps. And conceptually, it's really weird to think about that. But one of the things that you have to keep in mind here is that you also assume that T cold never changes. And neither does T hot. And the reason for that is that it's assumed that they have an infinite heat capacity. And of course, we know that that's not possible, right? That would either mean an infinitely large pool, or that something could take energy without its temperature changing. And everything that you've ever experienced with a fluid should tell you that that's not possible. If you're going to take heat from something, the temperature goes down. If you're going to give heat to something, the temperature is going to go up. And it also involves heat transfer, and you'll see this in a minute, between the system and the surroundings when they are at the same temperature. And as we've discussed previously, that's what allows it to be reversible. But also remember, we're chemical engineers, and heat transfer would be driven by the difference of the reservoir temperature and the system temperature. And if those are at the same temperature, what's the driving force for heat to move? There isn't one. And so it also would take an infinitely long time for this to happen. So there's a lot of really interesting simplifications in this cycle that make it physically impossible to implement. But what it does allow us to do is think about, in an ideal world, what's the best that we could ever do in converting heat to work, okay? And we're gonna sort of dive into that a little bit now. And some of what we'll do is a little bit of a repeat of things that we've done in the past, just to make sure that everybody's like on the same page. And then we're gonna end this by actually developing an expression for the Carno heat engine that's just a function of the cold temperature and the hot temperature, okay? All right, step one in the Carno cycle actually looks exactly like this picture that we've drawn. So step one is a reversible adiabatic compression from T cold to T hot. And so step one is a reversible adiabatic compression, okay? And in a reversible adiabatic compression, if you remember, our energy balance simplifies very simply, right, to delta U is equal to W, or maybe because we're going to have this for the world to watch if they so choose, du is equal to dw. And the entropy balance simplifies for a reversible adiabatic system to simply delta S is equal to 0, right? Delta S of the system. And so all the math that we've done surrounding this system is relatively straightforward. That, remember, this is CVDT, and that's equal to minus RT over V dV. Or if I don't skip the step, right, it's minus PdV. And then CVDT equals minus RT dV over V. And I'll divide both sides by temperature and get CV dt over T equals minus R times dV over V. And if I integrate from the initial condition to the final condition, we'll develop the same expression that we've had in our class a couple of times now. and that is that the integral from T1 to T2 of CV dt over T equals minus R times the natural log of V2 over V1, right? Or because you guys know that I don't particularly like to have negatives in front of logs, that's R times the natural log of V2 over V1. Now, if we have something like a simple ideal gas, we could assume that the heat capacity is equal to a constant, and that'll get rid of the R's. But I don't necessarily want to make that assumption right away, although we certainly know in the most idealized case here, we definitely have an ideal gas, and we said that already. So
Those should those V2 that V1 and V2 be switched on the second log?
yes, thank you. I'm sorry. I think I said V1 over V2, and then I didn't do it. But thank you. Yep. Okay. Oh, did I do it again? Sorry, guys. 1, 2. There we go. All right. So our first step is a reversible adiabatic compression. And I drew something that looked a lot like that already above, right? And that was here, right? That we had step 1 is this compression. And let's just say for a Carno cycle, let's take this with us. Okay. And we'll move it down here because actually we're going to end up following all of these steps that I drew. Okay. So step 1 was reversible and adiabatic. Okay. And it looks just like that. And so then step 2 in the Carno cycle is a reversible isothermal expansion at T hot. Okay. And so for that particular step, right, the energy balance is relatively straightforward, right? Because delta U is Q plus W, and delta U is equal to 0 because it's isothermal. And so the result of our energy balance for stage 2 is Q plus W is equal to 0. And our entropy balance, maybe EB is not the best one here, right? Because EB can also be entropy balance. So the energy balance is Q plus W equals 0. And our entropy balance, remember, we have a reversible system, so SG is equal to 0. And so our entropy balance simplifies to 0 equals delta S of the system minus Q over T surroundings. But remember, now in this particular system, we have to transfer heat because if we were going to do an expansion, the temperature would want to go down. So in step 2, if you wanted a physical concept of our configuration here, right? This would be hot, this would be cold. Our system would actually be touching the hot reservoir. And because of that, the fact that it's reversible, remember, the temperature of the surroundings and the system have to be the same. So this becomes T hot or Q over T hot. And so for these reversible isothermal expansions or compressions, actually, it would be at this constant temperature, right? So here Q is equal to T hot times the change in the entropy, right, between state 1 and state 2, okay? So for step 3, right, now we have added heat into the system, right? So step 3 is an adiabatic expansion to T cold, right? And that's even step 3 on the picture here at the top, on the top right. And this is where we're going to get most of our work out of the system. And because this is an adiabatic and reversible expansion, the energy balance is exactly the same as step 1, where delta U was equal to W, right? And so because of that, the integral from then T hot to T cold of CV dt over T minus R times the natural log of our volume here, right, over what I'll call V3, which is the state there, right? That's equal to 0, right, from our entropy balance. And so we have the same relationship that we had in stage 1, okay, between volume and the temperature. So the math in stages 1 and 3 are the same. And for stage 4, we now have a reversible isothermal compression at T cold back to the initial state. And think about this, when you do a compression, the temperature wants to go up. So how do we then stop it from doing that? Well, you have to remove heat. And we do that here by putting our system in physical contact with the cold reservoir. Okay. And the interesting thing is that steps 1 and 3 are physically isolated from these heat reservoirs. And in stage 1, we add heat, or stage 2, we add heat. And in stage 4, we're going to remove this. Okay. So if that's the case, the math is the same as stage 2. And actually Q in stage 4 equals T cold times delta S. Okay. Now, the interesting thing is that when you've seen cycles before, right, or at least the one time that we've had an example on it, that they look a lot like that, right, where you go around and you're used to asking yourself what is happening from the perspective of pressure, volume, and temperature. For some of these cycles, another way of thinking about this is also very helpful. And so we're going to draw something called a temperature entropy diagram. And it's helpful here because every step occurs at either T hot or T cold. And we also have reversible adiabatic steps, which are done at constant entropy. So we have 2 states of entropy here. And if we look at this, where the very first stage was a reversible adiabatic compression, right? So delta S is equal to 0. And we're going from T hot, from T cold to T hot. And so actually stage 1 in this temperature entropy diagram just goes straight up here, okay? Right, we're just doing a reversible adiabatic, right? Delta S is equal to 0 compression. So step 1, we go up. Step 2, we're going to transfer heat at T hot. And so we're going to go this way on this diagram to here, right? That's step 2. Step 3 is another isothermal, is another adiabatic step that's reversible. So delta S is equal to 0, except now it's an expansion. And so we go down to T cold, right, which is here, right? That's step 3. And then step 4 is this compression at T cold back to the initial state. So that's steps 1, 2, 3, and 4. And the interesting thing that I find about this process is that's very counterintuitive, that Q is exchanged in steps 2 and 4, right? but that's not when the temperature changes. So remember, in other lectures and other discussion sections that we've had, I've tried to be very clear about Q, W, and T really being disconnected from one another, that they're not as intimately related as you might initially think that they are. And here's a really good example of that, where we have these isothermal steps where obviously Q is exchanged or heat is exchanged, right? But the temperature doesn't change. And we're going to use that. We're going to use that to our advantage, because here, right, we would think, right, this is where we put heat into the system. This is where we removed heat from the system, essentially by putting it in contact with the cold reservoir. Step one is when you do a compression. So we might think of this as work that we had to do. And this is the work in step three that we want done by the cycle. And if we wanted to maybe think about this, really where we add energy to the process is only here. In a real cycle, W in is not real, because the piston cylinder is already going to be moving. So in essence, whatever we put in, we just simply can't get out. But there aren't two separate devices, right? It's just one shaft that's moving usually up and down in a cylinder, that that its momentum does work, then the combustion takes it away, right? Or the heat added makes it expand and keeps the process running. So if we wanted to think about it that way, we could actually define the efficiency. And the efficiency is just minus the net amount of work that we get out of the process divided by the heat that we added to it, right? Because the whole idea is that we want to convert heat into work. And if that's true, that's minus the sum of the work for the cycle, as I called it before, divided by, right, we added heat in step two. But remember that the sum of the work for a cycle is equal to, or minus the sum of the work of a cycle is equal to the sum of Q for a cycle. And we only added heat in steps 2 and 4. So that means our efficiency is simply the sum of the Q's for the cycle over the sum, or sorry, over Q2, which that equals Q2 plus Q4 divided by Q2. Okay. And that means that the efficiency for the Carno cycle is just equal to Q2, which was T hot, times delta S2, right, during stage 2, plus T cold times the change in the entropy in step 4, divided by the change in the entropy in stage 2 times T hot, right? And there's just one more thing that we have to look at, and it's the reason why the temperature entropy diagram is very important. So how are S2 and S4 related to each other? Well, if you look at that diagram above, right, where in step 2 we go this way, and in step 4 we're going this way to the left. But they're the same magnitude, and they have to be, because stage 1 and 3 are both isentropic. So that means that delta S2 is just equal to minus delta S for stage 4, or I'll actually implement it backwards, that that delta S2 or delta S4 is minus delta S2. And so that means our efficiency becomes T hot times delta S2 minus T cold times delta S2 divided by T hot delta S2. And all of these entropy terms cancel, and you get an efficiency that's equal to T hot minus T cold over T hot, or the Carno efficiency is equal to 1 minus T cold over T hot. And you're going to use this to your advantage, at least in the homework, and then for other examples that we're going to do. And this is the best possible efficiency. And it's the value to which all the other cycles will be compared.